Good morning, people. This is week 9, lecture 2. So, what I'm going to be doing today is two problems. One of them is from chapter 10, which is called the telescopic mechanism. And in there, you will see that, for example, the uh, uh, point curve joint and uh, spherical joint are going to pop up. And then the second problem is the universal joint mechanism, which is something like that. We're going to worry about this thing later on. Right now, I'm going to discuss the chapter 10. Here's the situation. We have two members. Let's say this is called the small link, and this is the big link, and one is inserted in the other one. And the bottom of this big link is is through a ball socket joint excuse me, or a spherical joint is attached to a point in the ground, and the top of this member, narrow member, is moving on this path. So as this thing traverses the path, at this point traverses the path, this guy goes up and down, and it telescopes up and down. Now, the only issue that we're going to have here is the fact that this member, if you're not careful, this member will spin about that axis. In other words, the first thing is that you should not make this thing a cylindrical joint. You have to turn it into a prismatic one, both of these. This has to be prismatic joint so that uh, that guy does not spin inside of this. However, the whole thing should be fixed because up here I have a point curve joint, down here I have a ball socket joint, and the whole assembly can actually spin. Assembly meaning these two pieces can spin about that axis. That has to be fixed, and that's the only real complication in the problem. Now, let me see now. Yeah, I'll call it out. Actually, this big one I call it outer. The slender one I call it inner. Okay, and let's go ahead and make it. Immediately I save this product file. So file, save management, save as. Let's see now my desktop, a new folder, and I'll call this thing telescopic mechanism. It's not a telescope really. Okay, like that, and save it. All right, so let's insert uh, let's first do the, the ground. The ground. Now, what I mean by the ground is that path plus a point down here. How about that? So let's go ahead and make a insert a new part in there. I'm going to call this thing the ground. Right click properties, ground, and ground. All right, let's make it. Okay, first a single point at, for example, 0, 0, 0. The location is not important, but I'll use the global origin right there. You can see that there's a point over there. And then up here, I'm going to draw a plane, which is parallel to, for example, this XY plane. And on it, I draw an ellipse or some curve. So on that, let me draw a plane offset from this plane. And let me make this thing about 4 inches high. Let's see where it is. So that's good. And on it, I'm going to draw It can be anything, but I'm going to make it an ellipse. Okay, let's see now, where is an ellipse? Right there. Maybe something like that. Exit. Okay, so you can see that it is like so. Okay, so there's my point, there is my ellipse, and then I'm going to make the other two pieces. So insert a new part over there, and I'm going to call it outer. Right click properties, outer, and outer. Okay, and by outer I mean, if you look at this configuration, this is the outer one, the one down here. Okay, so let's make it. So on a convenient plane, on that horizontal plane, I will sketch a little circle like so. And because it's hollow and the other guy, we wanted to slide on it. So exit, and let's pad it. Okay, so let me move this thing like, yeah, like that. Now, for a reason that may not be obvious to you right now, I'm going to make a point way down here, because at some point I'm going to coincide that location, that point, with this point. So I need a point down here. Okay, so let's make a point in the outer part, and it's going to be center of that circle, and we move on. Okay, so let's go and make the inner piece. We go out here, click on the floppy, so that at least this piece is fixed. Insert a new part in there, and we call it inner. Right click properties, inner, inner, and inner. Well, let's make it. Double click. Okay, so on a convenient plane, on that plane, or any other plane that you like, I'll use sketch. A circle that size, so why don't I just project that guy? There we are. Exit. Okay, and then pad it. Let's see. Yeah, okay, make it a little bit longer. That's easy to do. I just mirror extend it. Hopefully this guy can reach all the points in this ellipse. Actually, it looks like I maybe want to make it a little bit longer. Good. Yeah. Okay. Now, once again, because eventually I want to put the end of this inner piece on that ellipse. I need a point there. So let me make a point, and it is the center of a circle, and that circle in this inner part, we created a point right there. Now, let me uh, I was going to create a point here for you, okay, on that, because it is possible to put that point coincident with the point that I was going to make, or it is also possible to make that point coincident with that curve, either way. So I'm not going to bother unless I need it, I'm not going to bother. I'm not going to create my point here, okay? That's pretty much it. We go all the way to the top. and save it, save everything. Let's assemble. So first thing I'm going to do is I'm going to what is it? Anchor this ground. Okay, the ground, remember, is an ellipse and that point. Okay, so let's anchor that here. Good, it is anchored. And don't worry about the fact that the anchor is put up here, not at that location. It doesn't matter. These are both same part. Okay. All right. Good. Let's move these things apart. So I'm going to move that guy, translating direction X, and fine. Why don't we first? Let me also move this. Let me also move this. Okay. I want to make a prismatic joint between these two. So I need axis to axis and a plane to plane. As far as the axis to axis is concerned, it's very straightforward, that line and this line. As far as the plane to plane is concerned, while I have this thing, I can make that plane coincident with that plane, okay? Or I can make the angle, vertical angle of that plane and any other vertical plane of this to keep the same. I can use the angle constraint, or because of the way things are, uh, 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 coincident plane will also do the job. Okay, so update. This eventually becomes a prismatic joint. Good. It is a prismatic joint, but right now there are no joints, just constraint. And then I want to take this point and put it at that location. So coincident between, let me check that. That's a hassle. This point and that point. Update. Good. And finally, I want to take that point and put it on this curve. So coincident between this end point and that curve, and update. Good. So it's the kind of thing that I can check right now. If I go to move toolbar, manipulate icon, and say, okay, let's move, for example, let's move this piece in the x direction, and keep the constraints active right there. See that? With respect to constraint. So if I move it, you see it stays on that, and this guy telescopes up and down. So on surface, it looks like we're good. Let me cancel that. All right. Save everything. And now we're going to go to DMU kinematic, digital markup, DMU kinematics, the other way around. Okay, so let's get the magic wand. Here's the magic wand. New mechanism. Mechanism number 1, auto create. We say okay. So let's see what we got here. Definitely we should have a prismatic one. We have a spherical one down here. And it is possible for us to have another joint, perhaps another spherical joint up there. I'm not sure. Let's figure out. Yeah, two spherical joints. One is between the inner and the ground, and that's when I put this guy on that curve. That I don't want, because if it stays like it is, it's not going to move. So I'm going to delete that. However, don't delete the children. However, I want the spherical point joint at the very bottom, so that this outer tube can actually hinge about that. And a prismatic one, we know it goes up and down. One more thing, I need, notice that degree of freedom is 4. If I do a point curve joint, there's my curve, there's my point. Incidentally, if you had created a point here, done point, then you would have to hide that point and then select this probably. Notice that the degree of freedom is 2. in principle, it should be 1. The problem is that this whole thing, that guy and this guy, which is now prismatic, can actually spin about that axis, because this is a spherical joint, ball socket joint. Up here is a point curve joint. It is point curve, can still spin about that and be point curve. The question is, how do you get rid of that? How do you get rid of that 1 degree of freedom? There are many ways of doing it. This is how I'm going to do that. And there is a description of what my plan is right there. To eliminate the persistent degree of freedom, before you create, one way of doing it is create a point surface joint. But a point surface joint requires the point to be on the surface. So before you create that point surface joint, make sure that you create a point in the, for example, the inner part, which happens to lie on the plane, on a plane of the ground. And how do I do that? Notice what I'm saying. Create a point in the inner part, which lies in a vertical plane, for example, of the ground. The question is, how am I going to do that? So let's go back here. We're going to go to we're going to go to the ground. Okay, we're going to go to the ground. How do I do that? I'm sorry, we're going to go to the inner part right there. I am in the inner part right now. See, I double click on this. I'm in a part. I'm going to create a point on a plane. The question is, which plane? So I go to the ground and a vertical plane of it, not XY, vertical plane. Either this or the other guy, it doesn't matter. And this creates a point anywhere you want. This point is in the inner part, but it happens to be on the XZ plane of the ground. Okay, now go back to your DMU and create a point surface joint right there. Point surface. See that? Point surface. It says, what is the surface? Well, it's that plane that I used. It was XZ plane of the, I can't remember whether it was YZ or XZ. Oh, I'm pretty sure it was YZ. That point that I created was actually in the YZ plane. There is the surface, and the point is going to be from the ground. I have it here. You can do it either from the tree or just literally point it, select it. Oh, where is that point? Not this one. This guy. Because this guy is guaranteed to be in the ground YZ plane. Okay, all right? Not that guy. This point may not be in that plane, but this one is, because you just created it. And then say okay. And now the degree of freedom should be 1, not 2, 1, right there. You can see that, okay? Yep, right there. See, we already had the spherical one down here. We already had the prismatic one. We made the point curve, still came out to be 2, but we create a point surface joint so that this point always remains in the YZ plane of the ground. That means this guy can no longer spin about that. Now let's go make our point curve joint length driven. Very good. And mechanism can be simulated. And we can make a cartoon and putting the physics in it, getting graphs and things like that, you already know how to do it. Or if you don't, please go ahead and watch the first 2 weeks. Yeah. Let's create a mechanism. Now, this is right now, it's not at the 0, 0 location. If I want to bring it to 0, 0 location, let me cancel that. Let me cancel that. Manually, you go and bring it there. So this is the simulation with command. Right now, it's at that location. So if I wanted to start at 0, I bring it to 0. This is the 0 location for that. The only difficulty with this problem was the fact that you had to take away that second degree of freedom, and one way of doing it is exactly what I described here. Okay, good. So let's go to our next problem. It's a universal joint. Now, universal joints are used in order to transfer motion from one shaft to another shaft, particularly when these shafts are not go along the same axis, for example. If you go down here on Church, you can see these gigantic trucks have something coming out of their engine, which goes with a slanted shaft. It goes to the rear wheels, for example, and that's what it is. Now, the thing is that, uh, for example, this thing is attached to a motor. It turns at a constant speed, and this guy is rotates, but the speed is not going to be constant. So you're transferring motion. This has a constant speed, but this one does not. In fact, you can show that this has a fluctuating speed like that. So as this thing turns, this guy turns, or as this thing turns, that guy turns, but the speed is fluctuating. It's like that. This may be constant, but this guy is not. And the maximum for every rotation of this horizontal one, the other guy rotates twice. Okay, and that's what these things are saying. The angular velocity is actually, and the angular acceleration is has 2 cycles per revolution of the input shaft. And the maximum and minimum speed of these, the maximum and minimum values are determined by this expression. So if, for example, I have see, omega output over omega input is less than or equal to 1 over cos of angle, the angle here, and bigger than cosine of the angle. So if, for example, if angle gamma is 30 degrees, if this is 30 degrees, and the RPM of the input is is a constant RPM of 60 RPM, you output is going to vary between 69 RPM and 52 RPM. Just divided by cos of gamma, and multiplied by cos of gamma, you're going to get 52 and 69. Now, this obviously fluctuating speed is not acceptable. So what people do is they create what is called a constant velocity joint. So what they do is they attach another universal joint at this end, another universal joint at this end, parallel to the original one over here. So this is constant, this is fluctuating, but when it goes to the original one, the second one, the second speed becomes constant, and in fact becomes the same as the input shaft. Okay, so that's what the constant velocity joint is. That joint is also available in CATIA, but I'm not going to use it. I will be using universal joint. Now, let me see now. Now, the pin, it is not needed in order to transfer that motion, at least from the kinematic point of view. Okay, if you are interested, obviously, in the stresses in that cross pin, then definitely you have to model it. But if the whole idea is transfer motion from one shaft to another shaft, according to the laws of physics, that pin does not have to be modeled. Uh, I'm going to model it first, and then I'm going to show you that if you don't need it, you can just get rid of it and proceed with the rest of the problem. Okay, so here's what I'm going to do is I will create, in this problem, I will create a orientation, a dummy part, which is just shaft orientation. So basically a broken line like that, because it makes it easier for me to put these things assembled together. Okay, so I'm going to create a dummy thing, which is called shaft orientation, which is like so, and then shaft and the cross pin. This obviously is an instance of that. Uh, Either I make it or I use a copy of it. Okay, so let's go ahead and do that. I don't need this anymore. Let's start with the product file. Immediately save it. So file, save management. Save as on the desktop. New, let's see, a new folder. Let's call it Universal. Okay. So I'm going to insert my first part, which is the orientation geometry, orientation direction. What do I call it here? Shaft orientation. Okay, I'll call it shaft orientation. Insert a new part in there. Right-click properties, shaft orientation. Too much typing, so I'm going to copy and paste it. Right-click, copy, and paste it down here. Okay, let's go make it. Double-click on that vertical plane. I will sketch pretty much a broken line like that. And that angle, I'm going to make it 30 degrees. So dimension between this and that, it's 30 degrees. I'm not going to worry about the size here, so that's fine. Exit, and immediately you save this. Go all the way to the top. Oh, before I do that, for a reason that yeah, that's good actually. That's fine. That's fine. So save. Now I'm going to insert the shaft. So insert a new part in there. And I'm going to call this thing a shaft. Right click properties, shaft, and shaft. And we make it. Double click on this. So here's how I'm going to do that. On that vertical plane, I will sketch something that looks like that the grip of that shaft, the end of that shaft. So let's not worry about the actual details here. Let me try to make something that's reasonable over there, there. Okay, let's clean it up. First of all, I want nice and symmetric. The top control bottom, control this axis. I want it to be symmetric. Okay. Same thing with this control that, control this axis symmetric. Okay, good. And am I happy with this? Yeah, why not? Sure, I'm happy. Okay, exit. All right, and then pad it. Mirror extent. Maybe make it 0.3. See how it looks like. 0.2. I think that's good. That's good. Okay. Now on that top face, I want to make these holes because the cross pin eventually is going to go there. Fillet. Zoom in. Let me see how this thing is. Okay, so it looks like that. So I'm going to draw a little circle here. Exit. Okay. We pocket all the way to the end. All the way to last. Okay. And then the actual shaft is going to go on this back face. I will sketch. Little circle. Exit. Pad it. Okay. That's good. Now, for a reason that may not be obvious to you right now, what I'm going to do is I'm going to create a point which is exactly halfway between the top circle and the bottom circle. So how I'm going to do that? You do it any way you want. This is how I'm going to do that. Point between, this is between what? I want between 2 points. For the first point, right there, right click, create a point, circle center, that circle. There it is. Okay. For the second point, right click, create a point, this bottom circle. Okay. And it's exactly halfway, and there we are. You do it any way you want. Okay. Now, let's save everything. And what I will do now is to create my crosspin. So insert, new part, say no, right click, properties, crosspin, crosspin, crosspin. Okay, let's make it. We go here. On a convenient plane, on that top plane, I will sketch a circle that size, but we know how to do that. We're going to project that circle instead. I'll do it. Exit. Okay, right there, you can see that. And I'm going to pad it. Pad that circle that I just drew up to the bottom plane, up to last, and see if it goes. Well, let's go up to the plane, and select this bottom plane. There we are. And I want exactly the same thing at 90 degrees to that. And one trick to do it, you can do it any way you want. This is going to be circular pattern. So instances, angular spacing, two instances, 90 degrees. And the reference element is, for example, this line. And it's not the current solid. I just want that pad, okay? So I don't want this. Although you can see that it works too, but I mean, there's no reason to do that. I use the pad and say, okay, there we are. You do it any way you want. It's up to you. All the way to the top, all the way to the top. And all the way to the top so that you see the double gears here, right? Click on the floppy. Okay, good. Now, remember, this other shaft is exactly like that. So that being the case, what I can do, I'm going to say insert. After I say it, because I did save it, existing component shaft right there. Not shaft orientation. Shaft orientation was just that broken line. And we say, okay. And there's going to be another shaft sitting on top of this that we have to separate and then do the assembly process. Okay, good. So let me move these apart. Translate this thing in X. There's two of them. You can see that. All right. And let me move the crosspin also so that it doesn't distract me. Right there. And we say, okay. All right. So first thing we're going to do is anchor the orientation. There, this is anchor. Then I want to put that point right at that joint, at that location. So coincidence between this point and that point over here. Hopefully I did pick it. We can check actually to see whether I did pick the point between point and point. See that? And update, it's going to move it there. Good. And I want a coincidence between this axis and the axis of the cylinder. Zoom in if you're having a hard time. Because what I picked is not the axis of the cylinder, it's just the orientation. There's the axis of the cylinder. Obviously, there's nothing to update. Good. Now I'm going to have to do exactly the same thing on this side. So coincidence? Well, actually, yeah, let me do this. Let me rotate this first of all. Makes it easier if I rotate this thing about that line. Let me turn it. Good. And now coincidence between this axis and that axis, that axis meaning that guy. Very good. And why don't I bring this point and make it coincident with that fellow? So another coincidence between this point and that point. Okay. Update. Good. Okay, let's put the pin in place. Why don't I rotate this thing a little bit so that it doesn't block my view. All right, now let's go take care of the cross pin. Why don't we move this thing closer? Translate in direction X. Okay, good. Zoom in. Coincidence between this axis and that axis. Okay. And coincidence between this plane and the top plane here. Oops. I don't know what I picked. Yeah. This plane. That's going to become a revolute later on. And update. There we are. And now coincidence between this axis and that axis. Coincidence between this axis and that axis. Update. Very good. So let's see actually, why don't we save everything? Why don't we save everything first? All of the, well, click on the floppy, it will save it for you. All right. Let's see if this is working. So we go to move toolbar, manipulate. We do a rotation about that, and we grab this guy and move it. Oh. Remember, this has to be checked. Cancel. Start again. This has to be checked if you want to make sure that the restraints are all taken into account or the constraints are all taken into account. Rotate about that, grab that guy and move it. Ah, see? That's the way it should be. That's what the universal joint is. Let me cancel that. So hopefully we can do the rest of the problem. Good. So let's go ahead and go to a digital mockup. DMU kinematics, get the magic wand out, a new mechanism, mechanism 1, auto create. So let's see what kind of joints we got. There may be additional joints that we may have to delete. So let's see if you understand. First of all, this spherical one was created because I brought that point that was created and placed it right there. That spherical one I don't need. I'm going to delete. And notice that it doesn't even affect the degree of freedom. So we have uh, we have two cylindrical, two revolute. Let's check degree of freedom is 1. Let's take the input shaft. This is the input shaft, which was the first one, cross pin and the shaft. Not the cross pin, shaft and orientation. This is the one, right? Shaft orientation right there. And I make it angle driven, 0 to 360. And we say, okay, mechanism can be simulated. Can I make a simulation here for you? Well, first of all, if these planes are all blocking your view, you don't want to see them, no problem. So you're going to go to, you can go to tools. Where's that? Edit, to search, find all the planes. I'm going to hide them. Okay, find all the planes and we hide them. I'm going to type here planes and plane, and this means find and select. And then once it finds and select, you can right click hide, or you can just click on this icon down here and it will hide it for you. Up to you. There. This will hide it. Right there. Any sketch that you don't want, you can hide. Any constraints that you don't want to see, you can hide the whole thing. Right click, hide. It's a lot cleaner. Okay. Good. Yeah, we are going to make a simulation here. Mechanism number 1, say OK. And I drag this thing all the way to the end. Insert, change it to anything but 1, and play it continuously. There we are. Now, the purpose of this joint is transfer the motion here to the motion there. But that's what this crosspin does. But you might say, oh, wait a minute. Okay, I understand. I understand what you did, except that you didn't teach me anything new, because this stuff we already know. So what I'm going to do is I'm going to say, okay, why don't we get rid of everything that has to do with the crosspin? So this is the crosspin. This cylindrical one is crosspin. I'm going to either delete it. I can deactivate it. I'm going to delete it. Gone. Don't delete the children if you ever need those constraints. And there's another crosspin thing, which is right here. I'm going to delete it. Don't delete the children. So I no longer have something that I can simulate, because we could simulate, because that crosspin was there. We took that degrees of freedom away. So if you look at if you look at the joints that you've got right here, let's go through them one by one. Revolute, prismatic, cylindrical, screw joint, uh, spherical joint, planar joint, rigid joint, point curve, slide curve, roll curve, point surface. This is a constant velocity joint that I said I'm not going to. Oh, universal joint. Sorry, universal joint right there. This one we're not going to do. This is the one that is constant velocity joint. So basically two universal joints put together, and we have done these other two. This is a gear and this is a rack. So here's a universal joint, and look at what it says. It says, okay, let me cancel that. Try it again. It says, okay, spin one direction. Here's spin one direction. The spin two direction. Here's spin two direction. We say, okay, Notice that it can be simulated now. So let's try it. Let's try another one. We already have a simulation here. I can delete that or I can leave it. Let me delete this, okay? Create another simulation. Drag it. Notice that that pin does nothing. As a matter of fact, I can hide it. Drag this, insert, rewind, and play it continuously. That pin, plus pin, does nothing. Okay, now let's check these formulas, these things that I said. Let's put some physics into this. So you go to f of x, you click on the mechanism. There is your revolute angle-driven. This is the angle-driven one that you have, and you say add formulas. Okay, and so for example, I can say that angle equal to 360 degrees per second. By the way, you can type 60 turn underscore minute. That means instead of writing it 60 degrees per second, you can write it like that, times time. The time is here. Double click. You say okay. Good. Let's do simulation. Let's create a sensor so that we can see some velocities. For example, I can do this. Let's say I create a sensor here, acceleration sensor for that point. Okay, so let me select this corner point. Let me see if I can find a. Oh, not mechanism one. Oh, wait a minute. Selection point, right? For the reference product, I use the orientation shaft. Yeah. And for the point, I select this point. We say okay. Now we're going to go and do simulation with laws over a 1 second interval, not 10 seconds, 1 second. Activate sensor. For example, let's do the, I don't know, maybe the velocity of that point. So speed, magnitude of the speed, for example. Where is that? This angular speed. No, I'm not angular. I'm going to go. Well, you can do the angular speed if you want. Sure. Angular speed, fine. Turn per minute. Okay, no problem. Move this thing out of the way and play it. Yeah. And graph it. There. So you can see that during 1 second, the input shaft went once, but that output shaft has gone twice. And in fact, this number is 70, between 51 and 70. Do you remember that? Where is that? Right there. 52 and 70, 69. So there's the physics. Okay, so that's good. Everything went smoothly except for that telescopic mechanism, the location that I wanted to put it at the original. So I had to update the joint, which I didn't like it, but anyway. So everything went smoothly except for that one item. Good luck and see you tomorrow.